Hello guys, um, back again with me. So today we're going to study about the next topic of redox equation. So previously we have discussed about the electron transfer in ionic reaction. So in that case, determining the reduction process and oxidation process can be easy. But what about the reaction that involves the covalent bonds where there's no um, ion that is formed? For example, C plus O2 gives you CO2. In this case, to be able to determine which atom is experiencing the reduction and the one that experienced the oxidation can be a little bit tough because the electron transfer is not as obvious. So another method is developed to be able to be used in a case where where it is applicable in both ionic state and um, for covalent compounds as well. So the whole purpose of assigning the oxidation state is monitoring how electron density changes when the reaction proceeds. For this one, why we say it's electron density, because sometimes there's no electron transfer, but the density of the electron does change over time. And oxidation state made out of two parts. The first is the sign, whether it is the positive or negative, and the value, whatever the number is. So in this case, for example, Fe3 plus. Fe3 plus, sometimes it can be confusing which one is which one is the oxidation state and which one is the charge, because both have the sign and both have the value. So the correct way to write the oxidation state of iron here is plus 3. 3 plus is the charge, while plus 3 is the oxidation state, or it can be called as oxidation number as well. Why the two things are being differentiated? Because charge only happens in ionic state, while oxidation state or oxidation number can happen be it in covalent or ionic compound. Again, it is important to note the correct notation when oxidation state are assigned. The correct way is plus 3, not 3 plus. Sometimes the question can give you this common 4 option, which is plus 3, 3 plus 3, and Roman numerals 3. In this case, the only correct notation is just plus 3. So what does the positive and negative sign mean? So the positive and negative sign doesn't necessarily show that the atom has gain or lose electron, but it's the plus sign means that the atom has lost possession or control of electron. So although it is for covalent, we know that it doesn't possess less, it doesn't possess more, but instead the electron density decreases and it loses the control of electron, and vice versa for negative signs. Negative signs means that it gained the possession or control of the electron, while the value just indicates the number of electrons which the control or possession has changed. Remember that we need to write the sign first, then the value comes later. So the more complicated part of oxidation state is assigning the oxidation state itself. Um, in this case, there will be 4 slides um, explaining about how we should assign the oxidation number. It can be easy, it can be understood easily. The rule can be long, but when we about to apply that, it can be as easy as possible. The first is for elemental state, the oxidation state is 0. So again, we remember about elements. Elements is something that has the same atomic structure. All of the substance have the same atomic structure. So be it H2Cl2, it is an element. Even when I give you S8 or P4, because it's not bonded with any other different element, it is still an element, not a compound. So for any element, it's going to be 0. Second, for simple ions, the oxidation state is the same as their charge. Na plus is +1, and 3 minus is -3. Whatever the charge is, their oxidation state will be the same. The third rule is the sum of all atoms. Remember, all atoms in a neutral compound must add up to 0. So for example, if I have CO2, I'll just change the color. If I have CO2, means that the oxidation state of carbon, one of that, plus 2 times the oxidation state of oxygen will equal to 0. Remember that we have 2 oxygen on CO2, therefore we have to multiply the oxidation state by 2. And then the third one, and the fourth one, the oxidation state of all the atoms in polyatomic ion must add up to the same charge of the ion. So it's like the combination of the second rule and the third rule. The total of all the ions, all the atom in a polyatomic ion must be the same as their charge. For CO3, 2 minus, CO3, 2 minus, this is the correct one, not this one. So the oxidation number of carbon plus 3 times the oxidation number of oxygens, because we have 3 oxygens, will add up to -2, the charge. So in this case, we still look up on the overall the basic rules. Now we get where to the real calculation, the real number. In a compound, the most common oxidation state for a given atom is the same as the charge on its most common ion. So for example, group 1, because they usually form positive ion, the oxidation state is also +1. Group 2 is +2. Group 17, the halogens, is -1. Oxygen is -2, and so on and so forth. Now, this is where it gets a little bit difficult. Some elements tend to have different oxidation states depending on which element that are present in the compound. Some examples include the transition elements and nitrogen, phosphorus, sulfur, tin, and lead. So what are those? This is the more specific one. For fluorine, it will always have the oxidation state of -1, no exception. the other halogens is most likely to have the oxidation state of -1 except when bonded to oxygen or a halogen that is higher in the group. So for example, if the compound is Fi, we know that F is always -1. Therefore, the oxidation state of I will be +1 because the third rule, neutral compound must add up to 0. Or if it's ClBr, another covalent compound, which one is which? The more electronegative, or the one that is higher in the group, will possess its normal oxidation state, -1. Therefore, the Br will have the oxidation state of +1. The oxidation state of oxygen is usually -2, except when bonded with fluorine, the oxidation state is +2, or in peroxide. The formula of peroxide is O2, 2 negative. Therefore, each of the oxygen will possess the oxidation state of -1. The oxidation state of hydrogen is usually +1, except when forming hydride with metal, where the oxidation state is -1. All transition elements need to be determined on a case-by-case approach. So it looks like there are plenty of rules, and to be able to remember all of them can be a little bit difficult. So the shortcut is metal will always have a positive value of oxidation state. There's no way that a metal will have a negative value. If it's main group, alkali metals or earth alkali, it will always the oxidation state will always be the same with its ion. And the second rule is the more electronegative an element is, the more likely it is to have a negative oxidation state, and vice versa. More electronegative, negative oxidation state. I think that's self-explanatory. Now, let's do the exercises. Pause the video if you need time to solve this. Okay, let's do this together, and you can check your answer. NO3 minus. So we are using the fourth rules, where the polyatomic ions, the sum adds up to their charge. N plus 3O equals to -1. We know that generally speaking, oxygen will have the oxidation state of -2. 3 times -2 plus N equals to -1. N is -1 plus 6. Therefore, N is +5. N is +5. O is -2. The second one, OF2. We know that F is will always have -1, and oxygen, when bonded with fluorine, it will be +2. Third one, CH3MgBr, a very common reagent in organic chemistry called Grignard reagent. For this one, we can separate, we can do this one by one. We know that metal will always form positive. It's +2. Br is most likely to be -1. So we can fill it up, +2 and -1. Hydrogen is +1, and we have 3 of them. So C +3 +2 -1 equals to 0. C +4 equals to 0, therefore C is -4. NaH, sodium hydride, metal will always form positive ion. Sodium is group 1, therefore the hydrogen is -1, metal hydride. Hydrogen and hydride will form the -1. H2SO4. Hydrogen is +1, oxygen is -2 as usual, therefore +1, -2. We have 2 times +1 plus sulfur plus 4 times -2 must add up to 0. Sulfur -6 equals to 0, therefore sulfur is +6. Now we have NH4NO3, ammonium nitrate. To be able to do this, we have to separate that into NH4 plus polyatomic ion and NO3 minus. NO3 minus we have done before, NH4 plus and plus 4 times +1 should be add up to +1. Therefore N is -3. So the hydrogen is +1, oxygen is -2, and it can be -3 on NH4 or +5 in NO3. NH4 plus NO3 minus. And that's how you do an oxidation state. So, after knowing the oxidation state, how can we determine which atom undergoes the reduction or oxidation process? So, the oxidation process can be indicated by an increase in oxidation state and vice versa, while reduction process indicated by a decrease in oxidation state. Okay. Can you explain it in simpler wording? If the oxidation state is reduced, then it is a reduction process. Reduce, reduction. What about the oxidation? Reverse that. Okay. What about this? Which one is oxidation process? Which one is oxidation process? Magnesium, element 0. Oxygen, it's also an element, it's also a 0. Magnesium oxide, magnesium +2, oxygen -2. So from magnesium to magnesium oxide, it is oxidation process. Then from oxygen to magnesium oxide, it is a reduction process. The number is reduced from 0 to -2, that is why it is a reduction, while for magnesium, it's the number is increased from 0 to +2. What about this one? I think I will have to correct the I2 plus 2S2O3 2 minus becomes 2I minus plus S4O6 2 minus. Fill up whatever we can fill up first. I2 is 0, I minus is -1, oxygen is -2, oxygen is -2. So 2 sulfur plus 3 times -2 should be -2. This is for S2O3 2 minus. And then 2S should be equal to +4. Therefore S is +2. Now for S4O6 2 minus, four times the oxidation state of sulfur plus 6 times -2 equals -2. For sulfur, -12 equals to -2. For sulfur is +10. So sulfur, the oxidation state of sulfur is 2.5. The oxidation of sulfur is positive 2.5. Okay, so you might be asking, wait, is this an anomaly? No, let me explain first. The calculation is correct. We should have the plus 2.5. So why the decimal place? Because the individual partial charge of the 4 sulfur atom are not equal. So we know that we have 4 sulfur. They're not all the same. There's possibility that they're different, and it happens in a lot of cases. Therefore, the average, what we are measuring is the average oxidation state of the sulfur in S4O6, that is 2.5. And if you encounter something like this, it is totally normal. It's fine to have something like this. Okay, so when we have solved the oxidation state of all the atoms, we need to observe the atom that have different oxidation state from left to right. We can observe that oxygen did not experience any change. What changes is the iodine from 0 to -1, and sulfur from plus 2 to plus 2.5. For iodine, the number is reduced, so it is a reduction process. And for sulfur, it will be oxidized. In the next meeting, we will learn about how to balance the more complex redox reaction. So you have to be able to understand which process is the reduction and which process is the oxidation. And if you ask, sir, is that possible if I have both reduction process or both oxidation process? The answer is no, it's impossible. If you encounter something like that, there's a possibility that we were not calculating the oxidation state correctly, therefore we fall into a wrong conclusion. Okay guys, thank you. That's all for today, and I will see you around in the next time. Cheers guys, bye.